Okay, in this section, we talk about the solution in the form of Fourier series. This is the most simple example we will have. We consider a beam like this, okay? This is a very famous problem, a simple problem. So, for example, if you have a uniform loading here, we can compute the reaction forces RA and RB by the equilibrium relation. Here is 300, 300, okay, times 10 equal to what? To 3,000. And then this one plus this one equal to 3,000. Okay, it's pointing upward. And also we consider the balance of moment at this point. RB times the length is this, and this one in the middle times this one times the length is the resultant, and it's acting in the middle, so the moment arm is 5. Okay, so this is the moment of this distributed load. So by these two equations, we get RB and RA equal to 1,500. Okay, no matter how, this is an easy problem. It means that the resultant forces here are obtained. And then we use a free body diagram process to help us. Here, this one is this one. And then we cut a very thin layer here to get this free body. And at the right end, we cut a very thin layer to get this one. This one is this one. And then the main part is the middle. It's writing like here. Now, see here. In the free body, we have a distributed shear force here. And in the free body, we have distributed shear force here. We assume that the shear stress here is uniformly distributed. So T0 times the height, this length is maybe called the H. T0 times H equal to RA. So T0 can be computed. RA is 1,500. So divided by H is T0. In the same deal, TL can be determined. So T0 and TL are obtained. So they are not unknowns. And this is the major part we will study. See here, the distributed load can be acting here. Okay, can be at here. So there is one doubtful point. By calculating T0, we assume that the shear stress here is uniformly distributed, but actually this may not be true. The distribution pattern of the shear force here is unknown. Okay, we didn't apply any theory or calculations to prove that the shear stress here is uniform. So in fact, it is an unknown distribution. Okay, but we can assume that the shear stress here is uniform by the sigmoid principle we had talked about before. If we assume another kind of distribution, so long as the resultant force is the same, then the global behavior will be similar. So by such kind of argument, using the sigmoid principle, we can assume that the shear forces here is uniformly distributed. It doesn't matter. Okay, it doesn't affect the solution significantly. So we assume that the shear forces along this edge is distributed uniformly. Okay, in such kind of reasoning, we get TCO and TL. So TCO and TL are some given numbers. Okay, they are not unknowns. Now, let us consider a general problem. Let me emphasize. The resultant forces here, the reaction forces I and B, can be calculated by consider the uniformly distributed load. But if the distributed load changes to the triangular one, okay, the triangular distribution load, you still can compute the resultant forces here, the reaction forces here. So no matter what kind of distributed load here, you still can have RA and RB. It doesn't matter. I just give you a most simple one to illustrate our idea. Here we can change the loading to a triangular load, and we can carry out similar argument as before. So now let us consider a general case. In the upper part, on the upper part and the lower part, we have some given normal force, normal stress and shear stress. Okay, like this. P1 and Q1x are some given functions. And in the in the lower part, we also have some normal stress and shear stress. P2 and Q2 are also some given functions. But in fact, usually P2 is 0, Q2 is 0, and here shear stress is 0 too. Only this one is non-zero, okay? But in general, we can consider they are arbitrary. It doesn't matter. Now, on the top, y equal h here on the top, we get this and this. In the bottom, y equals 0 here, we get this and this one. And the left, x equals 0 here. Sigma xx equals 0. We have low tensile forces here. Yes. And also the shear stress is this one. And also, so we minus T0. But it doesn't matter. It's plus and minus depend on how you think about the direction here. At the right side, XL here. Sigma xx equals 0. Sigma xy equal to this one, okay, as before. Now we have the boundary conditions, and we want to have the stress function inside the beam. We don't know what is going on inside the beam. We want to find out. So inside the beam, we know that the stress function satisfies the biharmonic equation, okay? So we want to solve this equation. Let us try this. Let phi equal to big X and big Y, the multiplication of them. Big X is a function of small x. Big Y is a function of small y. Okay, and we put this into here. But before this, we carry out the differentiation. See, phi xxx equal to this one. Because see, here, this one, when you perform the differentiation x with respect to x 4 times, you get this. This becomes this one. But y still unchanged. Similarly, phi xx yy equal to x double prime y double prime. So this one put in here, this one put in here. So this one will be written like this. Okay. Now divided the equality, the left hand side and right hand side by the same amount of quantity. Okay, xy, and this one equals 0. And this one will equal this one. Let us do it term by term. This one divided by this, y and y cancel out. So will become here. And this one divided by here will become here. And this one divided by this one, x and x will be cancelled out. So y is remain. So this is this. Okay? We repeat the result here, right? Now we differentiate the left hand side and right hand side with respect to y. So this one becomes 0. And this one, this is a function of x. When it is differentiated with respect to y, it becomes 0. We have this, and this one, we have this one. this one, and this one have this one. Now we can rearrange our equation from here to here. Okay, we just move it to the left, this term to the left side, and then divided this term here. So this term, this term, this term. Okay, this term is this term, this term is this term, and this term is this term. Okay, and now this is a function of x. This part is function of y. There's no reason that they will be equal. A function of x equal to a function of y, it is unreasonable, except that they are constant function. Okay, the only possible way that this equality is true is this, that this one is a constant function and this one is a constant function. So this one equal to k and this one equal to k. Otherwise, a function of x will not be equal to a function of y. Understand? Okay, by such kind of argument, this one equal to k and this one equal to k2. So this one and this one written like this, and this one written like this. Okay, understand? We arrange the terms. Okay, now let us do some detailed calculations. We say we integrate. See, we have a differentiation here, so we integrate this equation with respect to y, little y. Then this one after the integration gives you this term. Integration gives you this term, and this 0 will become k star. This is the integration constant. Okay, and then we want to cancel out k star by doing something. Okay, we leave it here first. Okay, but we call 3.a here. What is 3.a? 3.a is this one. This equation is 3.a. This one is 3.a. We call it here. Okay, from this one, you understand this one is this one, this one is this one, and this one becomes this one. You move it to the left of the equality. Okay, so now we compare this equation with this equation. These are equal. These two terms are equal, and these two terms are required to be equal. So this 2k equal to this 2 times this one. So this one equal to this one, give you this one. Understand? And this one equal to this one, give you this one. Understand? By comparison. Okay? Now, this one can be written as like this. Okay? Okay, this is consistent with 3.11. Okay, it's like this. Now we differentiate this equality twice with respect to x, and this one become this one. We differentiate it twice. Okay, this one become this one, and this one become this one. But now k double pi equal to kx. So this one equal to k square x. If we replace k star, k double pi by kx, right? So this is kx, so it's k squared x. Okay, so we get this one. Now we put this term to here, so this one becomes this one. So this one divided by this one equal to square. Okay, but according to 3.14, this one equal to minus k star. So from here, we get this one. From here, we get this one. So we have proven that k squared equal to minus k star. Understand? So by this result, we can replace k star by minus k squared. We can erase this k star and replace it by minus k squared to get this equation. Okay, you put minus k, this one erased, and replace by minus k squared, and then remove this y here, and then remove here, and then you get this equation. Okay, this is the result, more more lit. Okay, this is a better result. Okay, so finally we get this equation and this equation. Okay, let us perform a summary. We have a biharmonic equation. We assume that the phi equal to big X and big Y. Okay, and big X satisfy this equation and big Y satisfy this equation. Now we want to do it, we want to solve X and Y step by step. See here, X function satisfy this equation, and this equation will give us three possibility of solution. We have already done this example before. In section 1.4, example 10, we have this result. Okay, by applying the boundary condition sigma xx equals 0, x sigma xx equals 0 at x equals 0 and x equals L, we can solve this function and get the eigen functions. Okay, let us do it step by step. Sigma xx equal to partial phi partial y twice. Okay, and this one, and then this phi equal to x and y, and then we perform the differentiation here to get y double prime. Okay, and then we put x equals 0 inside to get this one, but this function is not equal 0, so this one equals 0. Okay, the same deal, we get this one. So we have this condition and this condition. We put this condition inside here, okay, to get this eigenfunction and eigenvalue. We have done this before. We have also proven that this function equals 0 and this function equals 0. The only useful function is this one, and this one will give us this eigenfunction. We have done this before, so we will not repeat it here. The second part is we want to, the third part is we want to compute the big Y function. See, we had already solved this one. Now we try to solve this one. If we can have this one, then phi is done. Okay. So we say that k here equal to lambda n. Lambda n is this one because we have already obtained k. Yeah? This is k, right? So we have this new equation because this lambda, k equal to lambda, right? K equal to lambda square. And now this lambda, it depends on the number n. So this is lambda n. And we also call it yn. Okay? But this equation has been solved before. Okay? As this form. See example 5 of section 1.4. We have already solved this equation before. We get this one. Now we summarize our result. Phi equal to x and y, but x equal to xn, y equal to yn. So we define a new function phi n. Okay? And now apply the principle of linear superposition. We get a general solution. Phi equal to summation of phi n equal to this, and then this one equal to this one equal to this. Now, if we put C2's bar inside the bracket, and then we can, combine this constant with this one to get an. And we can combine this constant with bn star to get bn. Okay, like this, cn, dn, the same deal. So finally, we get a very beautiful expression of the stress function phi. Now we want to compute the unknown function an, bn, cn, dn inside phi by the boundary conditions. But this job has been done in the previous examples. Okay, let us repeat it here. Y equal x, we have the normal stress like this, we expand it in terms of Fourier size series. This is the Fourier size series. And then shear stress equals 0. And then at the bottom of the beam, these two are zeros too. See? This is the picture we have. At YH, we have the normal stress equal to minus 10x. This is a triangular distributed load. Okay, we have a Fourier series here. Okay, and then Pn after the integration will give us this one. See the example 14 of 15 in section 1.4. Check it out, 14 of 15. And then at the bottom of the beam, there's low stress. Okay. So we have 1, 2, 3, 4 conditions to compute 4 unknowns. And this has been done before, okay? To compute this, to carry out the calculations, we need to calculate sigma x, sigma yy, and sigma xy. Here I have made some mistake. This is sigma yy, okay? So sigma yy, sigma xy should be computed. We carry out the differentiation like this, okay, to compute the sigma yy and sigma xy because we want to apply the bounding conditions. So here, sigma xx, perform it, the differentiation twice to give you like this. Differentiate it twice to give it this. The y part doesn't change, okay? And this one, okay, this is the minus sign, and then we differentiate phi with respect to x, so this one from sine function become a cosine function, and lambda comes out once. And then we differentiate y here. This one become this one. Cosine become hyperbolic cosine become hyperbolic sine. Hyperbolic sine become hyperbolic cosine. And this term become two terms. Then this term become two terms. Okay. Once we get these two expressions, we can apply the boundary condition like this one and this one. Y 0 here, y equals 0. Sigma yy, this, and 0, 0, 0, 0, 0, 0, 0, 0. And then we get this one. So an equals 0. And in the same deal, y at y equals 0, we have the shear stress equals 0. We get the similar calculation to get this equality. But this equality has been obtained before in the previous examples. So please check it by yourself. I don't want to repeat the detail here. Okay, we had already using this condition before. Now, in the same way, third condition at the y equal h, we have the shear stress equals 0. We get this one. And we have already done such kind of calculation in the previous examples. So check it by yourself. And also at the for the final condition, we have this sigma yy equal to minus 10x. We have this one. Okay, and this one can be computed. And then we have this, and then we get a equation for Bn and Dn. Okay, so finally we get a small system of equation solving for Bn and Dn. We can get Bn and Dn. Actually, we can figure out all of this detail in the example 15 or 14 in section 1.4. Check it yourself. 14 or 15. Okay, so as a whole, we can obtain An, Bn, Dn, Cn without difficulties. Okay, so we can compute An, Bn, Cn, Dn without difficulties. So actually we can get phi. Okay, so this is a concrete example to show you how to compute a solution by using the Fourier series techniques. Okay, here phi is a Fourier series. Okay, so how this Fourier series can be obtained? This Fourier series is obtained by solving the differential equation like this. Solving this equation and have x and y, and then you finally end up with this Fourier series. And this Fourier series containing some arbitrary constant. And this arbitrary constant can be obtained by the boundary conditions. Okay? And once you get this stress function, you can compute the stress inside the beam. Okay? Inside the beam, you get the stress function. By using phi, you can calculate all the stress component inside the beam. Once you get the stress components, you can get the strain components, and also you can get the displacements. Okay.